So we talked about this one, yes? That one. That indeed these transformations make sure that this postulate, that the Minkowski line element has the same value for all observers, that is really true. So if you want to put it back there in a second, if you want to write down this question mathematically, then this is what's being asked. Here's Minkowski line element, and it should have the same value for all observers. So the other guy who was measuring his time with a prime and his spatial distances with primes should give the same number back. Right, this is really the question. That no matter if you are the guy measuring your time and your space, or let's be more puristic, your durations and your distances in prime coordinates, or that you're the person who's doing it in unprimed coordinates, you should get the same answer, even though the numbers themselves might differ from each other. These might differ, but this combination should be the same. And my claim was, well, this is the case if your primed coordinates and your unprimed coordinates are related in the following way. So here's a question mark, is this true? Under the condition that dx primed, well, let's start with dt primed. dt primed is gamma c dt minus b over c dx. This is just the equations that I just erased. That's the question. Is this true if this is the relationship between the primed and the unprimed? That's the idea. I was a little bit sloppy before when I gave you the Lorentz transforms. I should have mentioned explicitly that these only hold for two observers who are moving in x direction with respect to each other. In other words, that this v, right, that's their relative velocity, is in x direction. In y and z direction, this holds. So these sets of transformations only hold if the two observers are in x direction movement with respect to each other. The general expressions are very complicated, but you never need them. Because you can always, we already saw that you can rotate through space without changing anything. Remember that with the vector, with the 2 points in just xy space, you can rotate as much as you want without changing anything. It was already invariant under rotations. So that means that if you have a situation where two observers are not moving in x direction, you just rotate to a new coordinate system in which they are. So you can always rotate your situation such that you only have to worry about the x directions. So in a certain way, this is the most general way that you can write this down. But that's easy, because if dy primed and dy are already equal to each other, then their squares are going to be equal to each other. So with my red marker of cancellation, this one will be cancelled by that one, same number. That's using this one. And this one is cancelled by that one because it's the same number. And we only have to worry about the x and the t's. Well, that's just a matter of putting in these equations, yes, and just these two, just see what happens. So let me start with the right-hand side. RHS stands for right-hand side of my equation. That's this one. Right, the dy primed and dz primed have been cancelled. I'm just going to do some algebra, no physics, just putting in the formulas. C times dt primed, that's just this thing here. But you have to square it. So you have to square this whole thing. That gives you this. I'm doing this in real time, so if I make a mistake, feel free to correct me. You have to square this whole thing. That's this one. Put that one in. Minus the x primed squared, so that's the square of this one. You have to subtract from it. So there's that. Just use the formulas that were given to me. And now just have to do the algebra. Again, No physics, just mathematics. This is me just squaring this bracket. Give you this. And minus gamma squared, and then this bracket squared, that's dx squared, plus v squared dt squared, minus 2v dx dt. There you go.
So you substitute equations for the transforms?
Yes, yes. This one, I put this in, and this one, I put that in, and the rest is algebra.
Well, I put the Lorentz transformations in the longer equation.
Yes.
In the integral equation.
Yes.
Couldn't get anything.
Okay. Maybe it was an algebraic mistake. Yeah. I mean, I'm doing the same as you, as I can tell. Let's just see what happens. I hope you already see that this thing and that thing will cancel. Because it's 2 times v times gamma squared dt dx. That's exactly what you have here. Gamma squared 2v dx dt. But this one, minus minus, has overall plus. This one has only this one minus. There's a plus amount and a minus amount, same amount, these two cancel. What you can do now is take everything that has a dt squared together and everything that has a dx squared together. Again, just mathematics, just algebra. And just read off what should be in between the brackets. This one gives you gamma squared c squared, that's this. And here it gives you minus gamma squared v squared. This is me just reading off what should be in front of the dt squares. So that's that one and that one. Now do the dx's. This one gives you gamma squared v over z squared, and this one gives you minus gamma squared. You already see it happening here? Getting close, right? Because you can want again, no physics. It's mathematics. Take a c squared gamma squared out of these brackets again. So this has turned into this. Yeah, with good reason. I hope you see why.
You have a gamma factor again in the brackets.
Yeah, there's a gamma.
Well, inverse gamma factor in the brackets.
And there's an inverse gamma here.
Ah.
Check it out. Here's a gamma squared. That's this thing squared. Gives you 1 over 1 minus v squared c squared, which cancels exactly this 1 over 1 minus v squared c squared. So this whole part, by the definition of what gamma is equal to 1. So what I get is c squared times 1 dt squared. So I'm done with this part. Now this part, take a gamma squared out. Should be this. What would this be? By definition of gamma? This is minus 1, yes?
Yeah.
So this is minus 1. So plus minus 1 dx squared gives you minus dx squared. Now that's what I wanted to show. The question was, is it true that if you write for dt prime and dx prime these transformations, you just get back what is there on the left hand side? Well, I started with right hand side, put in these equations, did the math, and what I find is, hey, c squared dt squared minus dx squared, which is exactly left hand side. So apparently, these Lorentz transforms indeed make sure that both of them get the same answer, that the line element is invariant. And that was what we wanted to show. So I hope from now on you have no difficulty, believe me, when I use Lorentz transforms. They really, really work. Any questions about this? Yes?
Is it way longer to do the same but with the y and the z in terms of calculations?
You have to specify a question a little bit more. What do you mean by if you do it by dy and dz?
No, I mean like if dy and dz are not equal in this case?
Yes, yes.
Is it much longer?
Yes, then it will be much longer. But fortunately, and this is what I stated before I did the exercise, but it's important to repeat for a second. We already showed in the main lecture that the dx, dy, dz part, forget about the dt, just the dx, dy, dz, does not care about how you rotate things. So even if things are not entirely on the x-axis, you just rotate it such that the dy's are the same and dz's are the same. Now, you're free not to do it, but then of course your Lorentz transforms will look much more difficult. And proving this will take, this algebra is equally simple, it's just more of it. Right, so that's one. Just continue with this one, derive the addition rule. That's this one, yes? And I promise you, you only need the Lorentz transforms. Let me be a little bit more specific. We did this v plus u. The minus would work just as well, as long as you also put the minus there. Both of them work. The question is, can you derive this rule from these equations? Here you might want to think a little bit exactly what the dx's and dt's mean. So, want to work on this for yourself a little bit? Try it later? So where it comes from? We can do it, but let's just do it now. See what happens. Now, I told you before, and I want to stress this over and over, in relativity, special and general, you have to be extremely careful that you properly define what you mean by all these objects. Now, what I prefer to do when I do exercises is really properly define two events. So I know what dt means, the time between two events, and I know what dx means, the amount of distance between two events. Now, which two events doesn't really matter, but I'm going to go with the flying bucket one, because that's what I used when we talked about this when we did the whole, do you remember, special relativity part. So we have a flying bucket, and there it goes, it's flying along, right? And I have to define two events. And we're going to talk about how fast a thing is going. Now, if I want to go how fast something is going, I have to measure how many meters it travels in how many seconds as seen by me. So what I'm going to do there's this niche here at the end, so you have these two walls that stick out. The bucket is flying by, passes that one end of the niche, that's moment one or event one, and at some point it will pass the other niche, that's event two, just to have a visual interpretation of what dt and dx means. So that's my flying bucket situation. I want to know how fast that bucket is flying by. Let's call that number u. I'm not going to use v because I reserve v for the velocity between two different observers, not the velocity of the bucket. So I'm going to use u. And in special relativity, just as in the rest of physics, velocity is just the amount of meters that something flies in how many seconds. So this amount of meters, and I just measure how long it takes, that's this number. Now you have this other observer who is also looking at that same bucket, the same two events. Let's make it either her. She is also looking at the flying bucket, and just like me, she's going to check in her frame when the bucket passes that part of the niche and the other part of the niche, right? You have to look at the same two events the Lorentz transforms only work if you look at two events as seen from one person, one perspective and the other perspective. You're not allowed to change events. So it's the same moments. The moment that it passes that part of the niche and that part of the niche. The moving observer should be more careful. The person who has a relative velocity with respect to me is also checking when the bucket goes by that point and goes by that point. And because she's walking along with her origin frame, what's the word here? The coordinate frame, with her in the origin walking along. So do you think is that a bigger dx for her prime, dx prime, or a smaller dx prime? The bucket is flying that direction. She's walking along with the bucket. Different velocity, but she's walking along. Bigger or smaller? Smaller. Exactly. Yes. All right. So we're going to do this. She also measures when the bucket passes that point and that point. That will give her dt prime. And for her, the velocity that she measures, well, just like anyone else, is just the amount of distance she sees between the 2 points divided by the amount of time that she sees between the 2 points. So that will be this. We called it W before. Okay. My question now is, how is W related to U? And we already know that there's probably some subtraction going on, right? Because there's less amount of meters between the 2 points. So she must see the bucket fly with a smaller velocity than me. To her, the bucket moves less meters because she's walking along with it. Yeah, just like the car in front of you is not going as fast, regardless of you if you're driving behind it, compared to when you were standing still next to the freeway. So let's do this. So that's the physics. Here's the algebra. Because I know exactly how I should relate her amount of space to my amount of space. And I also know how to take my amount of time, excuse me, her amount of time, and relate it to my amount of time. This is what the Lorentz transforms tell you. Well, we just proved in the previous exercise what they look like. And that they agree with the invariance of the Minkowski line element. So we're just going to put in the Lorentz transforms. I know how to write this in terms of the unprimed coordinates. dt. We proved it in the previous exercise. Now dt primed, same thing. I know how to write this in terms of dt and dx, the unprimed coordinates. Minus d over c squared dx. Right? We proved this in the previous exercise. This one goes to this, from one observer frame to the other. This one goes to that. That's all that I'm doing.
Sorry, just
Should it be squared?
Yes, they should be squared because the way that I wrote it before was dt primed.
Oh yeah, of course. Yeah.
Gamma c dt minus v over c dx. And I don't need c dt primed, and I just need dt, so I've divided c away. Gets it away from here, there you go, there's a square. That's what I did.
Oh yeah, fixed.
Yes.
Just conceptually, the v
Yes.
is that the velocity at which she is moving,
With
or
respect-
her reference frame is moving
To
with
me.
respect to you.
Yes.
Okay.
So the v has nothing to do with the bucket. The v has how fast she's moving with respect to me. Again, just algebra from now on. We've put in the physics. That was this step. The rest is algebra. Red marker of cancellation. The gammas drop out. And a very mathematically puristic person will come by and say, wait a minute, can you just divide gammas away? And the answer is yes, unless they're 0. Because you cannot divide zeros away just as easy, right? But then again, gamma is always 1 or bigger, so don't worry about that. So let's continue with the algebra. No gammas anymore. I get this. Now, if I massage my algebra a little, I should be able to make this in terms of u's. Because I know what u is dx over dt. My dx and my dt. Well, this is all in my dx and my dt, so I should be able to squeeze this in such a way that the u comes out. By squeezing or massaging, I don't mean that I'm smuggling, I mean this is just algebraically correct. So one way that you can do this is, you know what? In the numerator, I'm going to divide out 1 dt. It will give you dx dt minus v. Again, no smuggling, just algebra. If you multiply this back in, you will just get this again. And let's do the same thing for the denominator. Take a dt out. It's algebraically allowed. Let's just do it. You get this. If you don't believe me, just multiply this out, you will get this back. These cancel. Unless they're 0. The bucket is at both positions at the same time. You can ask yourself, is it possible for some observer to see the bucket at the two locations at the same time? Maybe intuitively you would say, no, that's impossible. And your intuition would be right. You can play around with the Lorentz transforms. You can prove for yourself that it's impossible for any observer to see the buckets at the same locations at the same time. Or maybe you can already see why without doing all the Lorentz transforms.
It violates causality.
You know what? I'm actually going to go with that. I want to phrase it in a different way, but it is correct. You're correct. The way that I wanted to put it was, well, we know that for any observer, either one of these two or some third observer, this should hold. This should be the same number for everybody, right? If I want these two numbers to have the same to be at the same position at the same, to be there and there at the same time, then this is 0. We get a negative number out. Whereas this number at this side, you can prove is a positive. Because this, as you remember, is always the amount of time for the other guy. And the amount of time for the other guy squared is a positive number. In order to get the distance then, you have to take the square root of a negative number, which doesn't give you a, well, I mean, mathematically the thing exists, it's this I times something, but you would get a complex amount of distance. To put the same conclusion into more physical terms, in order for some observer to see the bucket at these two locations at the same time, the amount of distance for that observer between the 2 points should be I times something, which is physically impossible. In other words, we don't have to worry about this, dividing these two because dt is not allowed to be 0. But maybe your intuition tells you the same thing, that things cannot be at two locations at the same time. So
There's optical effects where you can see things in locations.
Sorry?
There's optical effects where you can see.
Okay, but that's optical, because now we're putting in some, how would you measure that thing, and we give you an optical illusion. But everything about this is completely free of how I measure these things. So I'm sure we can set up that thing that via some light rays that get to your eye, it looks as if they're at the same location at the same time with some clever mirroring or something. But that's really just us squeezing in all kinds of optical effects. This is optical effect free, this conclusion. Yeah, but now I'm there where I wanted to go because I get my dx dt, which is my velocity. How fast I see the buckets flying along. So I get u minus v. There you go. Oh yes.
But there we have u minus v. No,
you know what? You're exactly right. So that probably means that your calculation was correct. And when I took notes at the beginning, I accidentally put them in the wrong order. And I'm going to blame Nelson because it was Nelson who gave me this equation, right? He dictated it. It was his fault. No, it was my fault. I should have corrected it, but it sounded right. So I decided.
Could have started with the alphabetical order.
Oh, you know what, Nelson? Let's save ourselves some embarrassment here and say that the way that he dictated it to you, there was a plus sign, and with plus signs, but it really doesn't matter what order you do them, right?
Mm-hmm.
Okay, so we're safe.
I only said plus.
That is true. It was my minus. Oh, it's all my fault. Okay, that's true. Okay, so your calculation was probably correct. Okay, so what I have here is that if you know how fast the bucket is moving as seen by me, that's the number u, and you want to know how fast the bucket is moving with respect to that other person who is moving with velocity v with respect to me, then it's this number here. So you can take my measured velocity, subtract our relative velocity, divided by this thing, and you get that number out. Yes?
So we did now the minus version, but how can you get into the plus version?
Okay, that's a very good point, because the way that it was dictated here, I'm not blaming anyone here now, but there was with a plus sign, and I derive now with a minus sign. Who knows the answer? Is there a contradiction going on, or is... Right, I mean, we did the velocity addition rule, and as we gave it with pluses, and now I do the derivation, it gives you a minus. So
Is there any way you can show that those two forms are mathematically equivalent with pluses and minuses?
yes, but they're not.
The point is to derive it though.
Does it have to do maybe with how you define your v? Like what direction you define the
Yes,
relative?
that's all there is to it. Remember, at the beginning I said, let's assume that the second observer, the lady, is walking along with the bucket. So that her total amount of the velocity that she sees must be a smaller number than I'm seeing, because she's moving along with the bucket. It must be a smaller number. This is why you get the minus sign out. If she would have walked the other direction, the bucket is flying in that direction, she's going that direction, she would have seen a bigger amount, because she sees the bucket move more meters with respect to her. The bucket's flying that way, she's moving the other way, so that the total amount of meters is going to be a bigger number. You would have gotten the plus sign. Now, then why is it if I put in my Lorentz transforms, I mean, I hope you understand that this works in both directions, would also work with the plus. It just depends on if the second observer moving along with the bucket or the other way. But why is it that this gives me a minus sign? Am I missing something here? Again, we understand this physically, but our mathematics just seems to give us just a minus, not the other possibility, namely the plus.
I mean,
Just define it as being a plus and negative number, and then derive it like that. See how it changes.
Yeah, we could do that.
Pretend that it's a negative velocity and then just do the same derivation.
Sure.
But do it the same.
We could do that, and it gives us back the same conclusion. It really just matters if the other observer is moving along with the flying thing or moving in the other way. In the Lorentz transforms, remember that previous exercise when we showed that the Lorentz transforms work? If you go through that exercise again, but now with plus signs, previous exercise, you will see that still works. Maybe you can already see why. You have to square everything, and that makes the pluses or the minuses squared give you pluses back. If you don't believe me, if you don't have that overview right now, just look at the calculation of the previous exercise, replace all the minuses with pluses, it would still work. So there's really two sets of Lorentz transforms. One, if in case the observer is moving along, and the other case if it's moving backward. I proved it for one, but it works for both. So you might as well write a plus and a minus here, as long as both of them are plus or either both of them are minus. And those plus and minuses carry over to here. And when Nelson dictated his version, he took the plus version. And my derivation started with the minus version. So that's why it seems a very contradiction. We're not. Plus and minus both work. So there you go. Well, now we're at it. By the way, we have now solved this one. Now we're at it. I said at the beginning, you can derive everything from the Minkowski line element and the fact that this postulate says that it should be the same number for everything. Note that I haven't put anything else in there. Sure, I talk about the flying bucket and pushing up students, but this is just me giving illustration of the situation. What I've put in mathematically is just the Minkowski line element, and that's invariant. We derived in the previous exercise this set of rules, the Lorentz transforms, and from this set of rules we get this. So everything just follows from that one invariant line element. That's all that I put into it. The rest is just mathematics. So this is also just mathematics. Now, another claim that I made was that if you have this postulate, this Minkowski postulate, it should ultimately give you back the postulate that people usually have in mind when they think of special relativity, namely that the speed of light is the same for all. We're now in a position to just check that. This looks familiar to the electrodynamics people, yes? But we can do it again, because it is very insightful. Just to show, just to make full circle, with our postulate starting from Minkowski line element to the one that you're more used to, namely that everybody sees the speed of light the same value, we can just prove that now. Instead of a flying bucket, we're now going to use a flying ray of light. Special case, not a flying bucket, a ray of light. I measure how fast the ray of light is moving over there, and I find that the number is 300,000 kilometers per second, c. Right? So I measure that this is the case. Now if you put u is c in this equation, I can calculate how fast that lady will see the same light flash flying by. We can just calculate, just put in the c for u, just see what happens. Again, it's just mathematics. So this u is going to be c. I'm going to leave in a plus and a minus. This conclusion will be true regardless whether the lady is moving along with the light or in the other direction of the light. You get this. I'm going to leave plus minus in. Agreed? Just algebra. I took a c out here, and then I put the c in front. You will get this. I see a number here, and I see the same number here, regardless of plus or minus. Cancel out, cancel out. Conclusion. If one person sees something move with the speed of light, then the other person will as well. And you see that how fast the other person is moving with respect to me is completely irrelevant because the v drops out. So that lady can run as fast as she wants, either along with the light or the other way. She will still measure that light, go with the speed of light. We've now made full circle with two sets of postulates. I took my set of postulates, did the math, and I get back the invariance of the speed of light that other people usually take as their postulate. So you now see that that person, that hypothetical other lecturer and me are really talking about the same thing. They're all connected to each other. Yes?
If the speed of light is invariant, no matter what the kinetic state of the observer is,
yes,
then how does the Doppler effect happen? How does the property of the light wave of the electromagnetic wave?
That is an extremely good question. Yes.
Due to movement.
I agree. That's a good question.
Because the crest of the waves get compressed or...
I agree. Yes. Does everybody understand the question?
Okay.
Right?
Can you repeat it?
Redshift.
That's just the velocity, but that's change the property of the light that's associated with the velocity. So it doesn't violate this, but it's still...
There's a short answer and a long answer. So the question is, I'm going to give you a short answer. The question is this. If you know your Doppler effect, then you know that if you're moving with respect to a source of light coming towards you, you will see some changes, right? The color will be different. If it's moving towards you, it will become more blue. If it's moving away from you, it will become more red. But my claim here is not that the color stays the same. My claim is that regardless of the color, it will still go with the speed of light.
I guess the frequency changes.
The frequency changes, but its velocity does not.
Okay.
That's the short version. The long version is that there is also a combination of the Doppler effect, changing of the color, and secondly, of the speed of light, and that gives you the so-called relativistic Doppler effect, which is a relativistic version of the Doppler effect. But that's the long version of the answer. Good question though. Yeah, but it's important to understand the frequency changes, the speed does not.
And so the frequency is determined by the velocity, so...
Yes, they are. That's true, because c is the velocity, is the frequency times the wavelength. But this has to be the same. This changed due to Doppler, so the wavelength changed accordingly to make sure that this stays the same.
Doesn't the wavelength change because of space?
Okay. We're mixing up a couple of different but very related concepts. What Paulus was talking about is there is space in which there is light, and you happen to be moving in that space. Then you see a shift in the color.
Yeah.
Okay, that's the Doppler effect. Then my claim is, I just erased it, the relationship between the speed of anything, or a wave, light in this case, is the frequency times the wavelength. This changes due to Doppler, so this changes accordingly. Now you come along and say, but wait a minute, I thought this one also changes because of the expansion of space.
Yeah, I was like, okay, if that's how it changes.
That is true. No, that is not true.
No?
No, there's two reasons for lambda to change. One of them is because of the normal Doppler effect that changes this number, and this has to change accordingly to make sure that C is still the same as we calculated here. That's one effect. But lambda can also change, it's a second additional effect, by the expansion of the universe. So there's two reasons for lambda to become bigger and bigger. One of them is simply because of the Doppler shift and it has to compensate, and the second one is because of the expansion of space. So there's two Doppler shifts really for light. One of them is called Doppler, and the other one is called the cosmological redshift. You can see that they're related. Both have something to do with lambda changing, but the cause is different.
All right.
We use the second one to measure the. Is that what we use to measure the distances?
Yes. Yes, that is his version.
They're the same.
Yes. Okay. So we've now made full circle. If you're ever in doubt whether these two sets of postulates are really the same thing, they are, because I've taken my postulates and I've proven the other ones. So we're now full circle. We have everything combined now. So that's good. We have now proven this. So we're almost there. All right. How's our time?
40 minutes.
Okay. Right?
Sure.
And try one of the physical exercises.
Yeah.
Sure. Okay. We're making good progress. Look at us. People, I propose to let you work a little bit on exercise 13 of the physical exercises. 2 is just as interesting, but 13 is just so that the connection is better to what we've been talking about now. And you can use my book if you want. And careful, because it's falling apart because of frequent misuse in the last decade or so. No, just writing.
Oh.
You don't treat books like that.
Oh.
Really?
Or your fellow man, really.
That's what it should look like if you really use them, right?
Yeah, exactly. This means that the book has been used. It's battle scars. No, 13 has a better connection to the details we've been talking about now, so I prefer to do that one. I think we should be able to finish that one up before the end of the tutorial. About 10:02 or so, I will take over and go through the exercise. Oh, by the way, sorry. One more thing. Remember over here when I said dx can be written as the Lorentz transform and dt can be written as the Lorentz transform? Just a question of checking. Why didn't I use time dilation to write this dt as the other dt? Right? It was time dilation just says one guy's duration of time is gamma times the other guy's duration of time. I did not use that one. I took the full Lorentz transform. Why didn't I use just the time dilation one?
Isn't it because the Lorentz transforms are derived from the line element and time dilation is inherent to that?
Well, it is very much true that this one has time dilation built into it. Both of them come from the line element. So in that sense, there's no preference for one or the other. It has to do with the setup of the
more
question.
general case, right?
Yes, but why can I not use a special case, a time dilation case?
When
does the special case of just time dilation apply?
when they don't have a relative, no way.
In this case, both observers can be moving.
Okay, that's the answer. Time dilation.
Wait, can you say that again?
In this case, both observers can be moving. So you use the Lorentz transforms, not the time dilation.
Remember this, time dilation only applies if one of the observers sees the two events at the same location. In this case, none of them did. because I, the standing still guy, saw the bucket over there and over there. That's not the same location. And the other person who was moving also did not see it at the same location. This is why it did not apply. Just as a check. I said before, in doubt, use the Lorentz transform. That always works. Okay, sorry for that interruption. You feel like trying number 13? Let's see. They say two things happen. Take your exploding firecrackers or something. And there's one inertial frame in which they happen at the same time. In that word simultaneously, you know exactly what the dt is in that frame, namely 0. And they also tell you in that frame what the dx is. It's 3 meters. Right? It says in an inertial frame, two events occur simultaneously, so dt is 0. Two events happen at the same moment. And at the distance of 3 meters apart. So if you would measure where the one firecracker explodes and the other one, you have 3 meters. So that's really just this situation again, one firecracker. Here's another firecracker, same that we've used many times before today. Standing over here, and they explode at the same time. Bang, bang. That's it. And it should be 3 meters away, should be about here-ish or so, something like that. That's the situation. Explode at the same time. Bang. Both of them. Okay. Now what they want to, what they then tell you is, there is another observer in a different frame, make it her again, and she is moving with respect to me and the two exploding firecrackers, and for her, the two events, explosion, are not simultaneous, but happen a certain amount, 10 to the power minus 8 seconds apart from each other. Question is, how many meters is the distance between the two? And the exercise asks you to do this in two ways. One of them is by using your Lorentz transforms. It's a difficult way of putting it, but they say, well, find your Lorentz boost. Lorentz boost is just terminology, it just means Lorentz transform. So by using the Lorentz transform equations. And the other one is by sidestepping the Lorentz transforms, going back to the original starting point or postulate of the invariance of the Minkowski line element. Now, both of them will give you the same answer. Of course I will, because the Lorentz transforms come from the Minkowski line element. We proved that today. So, if time permits, we're going to do both. So, two observers. Observer 1, the one without the primes. I hope you understand there is no physics in which one you call primed, which one you don't call primed. It's really just a distinction from each other. Now, I call the guy who sees them simultaneously, I call that one the unprimed one. This is the amount of time between the two exploding firecrackers. The amount of meters is some number, 3 meters. Then there's the other observer, the lady observer, and her I'm going to call by primes, and for her they tell you what dt is. It's 10 to the power minus 8. Right? If she looks at two firecrackers, the exercise states they are 10 to the power minus 8 seconds apart from each other. And the question is, oh, there's a prime. What is this number? That's the question. Now you know that the number must be different because you know that this thing squared and this thing squared in some particular combination should give you the same number as this thing squared and that thing squared. So you can just do the algebra and find what that thing is. That is the second way, by using the Minkowski line element invariance, but they want you to do it by Lorentz transform as well. So we're just going to write down what the connection is between these coordinates and these. And I hope at some point you will just know this by heart. That's this. Look at me not knowing them by heart. I think this is it, right? This is one of them. And this is the other. Just plug in the numbers. There are two equations, and that's good because if you think about it, we also have two unknowns. This number we know, this number we know, this number we also know, this number we don't know. They've never specified how fast they're moving, the two observers, with respect to each other. So here's one unknown. The other unknown was this number. But fortunately, we now have a system, an algebraic system of two equations and two unknown numbers. Just from your mathematics, you would know how to solve this. So it's just now a mathematical exercise. So let's start with this one. One with numbers plugged in will give you c times 10 to the power minus 8. I hope you see now why they put 10 to the power minus 8 here. So it balances out that c is 3 to the times 10 to the power plus 8. So they've made it such for you that this is a very convenient number 3. Alright? There's a gamma. Note in the gamma is that same unknown v hidden somewhere. Alright, so the algebra might be a little bit cumbersome, but it's in there. There you go. C dt. That's 0. C times 0 minus v over c times dx, and we know that number, that is 3. Question, what should phi be in order to make this work? This ultimately is what they're asking of you. Solve this equation for v. Now, this is just an exercise in algebra. Yes?
I have a different. I have
Okay.
used the Minkowski in the applied line,
Yes?
and since both of them are like have the same result, then I just put one is equal to the other.
Oh, equal.
And
No.
since
So that's the second way of doing it.
Yeah, Louis, that's
Yeah.
fine.
Ah,
But they
okay.
want you to do the exercise in 2 ways. I would go with your
okay,
way because that is
that's
much
it.
faster.
Yeah, that's what I.
But they want you to do
Oh,
this
okay, I
way as
didn't know
well.
that.
Now, if you read the exercise, you will see that they ask do it in 2 ways.
You're showing both.
And but did you get the number by the way?
No, I didn't calculate it, but.
Okay. Well, we should win. Let's take it as a test that we should get the same number.
Oh, I didn't know that there's
Right.
2 ways.
Well, there you go. Here's c, and that's itself 3 to the power minus 10 to the power minus 8. So if you plug in that number here, you get v over 10 to the power minus 8 cancels this 3 over there. I think this is correct still. And or if you will, 3 equals minus gamma 10 to the power plus 8. That's a ridiculously big number, by the way. Did I miss a c somewhere? Just a little surprised by the bigness of this.
I think it's just like you said that it's 10 to the minus 8 and it's 10 to the minus, it's 10 to the 8. So
They add minus sign.
Yeah, no, yeah, sure. Now I know why it happens mathematically. It's just physically I find it's a big number. But then again,
no. I mean, just above that, no, below. Yeah, that one.
okay, yeah.
That one should be 10 to the minus.
Plus 8. Thank
8,
you.
yeah.
Oh, there you go. Okay, good. Thanks. Good, because I know that this must be a very big number. They have to have very high velocity with respect to each other to see any relativistic effect at all. So I knew that v has to be c-like-ish. So v already should be 10 to the power 8-ish or something like that. And I thought times to the power plus 8 which I had. That sounded suspicious, but you're right. I messed up my pluses and minuses here. Okay, now this is an exercise in algebra. Okay, I don't know the number by heart. Shall we just go through the algebra just to see it work?
Sure.
Again, there's no physics now anymore, right? This
C
is just
3
doing
times
algebra.
10 to the power of 8. So you
So there's
so C
3
is 3
equals.
times the 8 and it cancels the 3 and the 3. So then you're just left with 10 to the power of 8.
So I just plugged in that I know what gamma is. I have to pry v out. Now, one thing I can do is square everything, so I get rid of the gamma here. Not the gamma, but the square root in the gamma. So it gives you 9 equals v squared 1 over v over c squared 10 to the power minus 16. I've now squared everything. Next step, again, this is all just algebra. There's no physics whatsoever in what I'm doing right now. Still okay with this? Here's the denominator. I multiplied both sides by this denominator. Gives me this. Work out the brackets. 9 times. Let's do it like this. Still agreeing with this? Again, just algebra. And now I'm in the happy situation that I see a v squared here and a v squared here, so I can just group these two together. In fact, c squared is 3 times 10 to the power plus 8 squared. So that should give me 9 minus the 3 squared in the c here will cancel this 9. Will give me v squared times 10 to the power 16 equals 10 to the power minus 16 v squared. How's this? From here to here I've just plugged in that I know what c is. I think this is still correct.
Yeah, is it though?
Well,
shouldn't
it's
it be
minus
power
16,
minus
right?
16 on both sides.
yes, because I'm messing up my
Yeah.
minuses again, yes. The same mistake twice on the same board.
So we have to do the 9 and the 9 over.
Well, the c contains a 3 to the times 10 to the power 8. And I have to square that thing, so that 3 in the c becomes a 9, and that cancels that 9. And the only thing I'm left with is 10 to the power something, and then I messed up my minus sign. Alright,
Thank you.
continue here. I see that 9 should be equal to 2 times 10 to the power plus 16 v squared. Or in other words, v squared, well, you know how the rest of this goes, yes. Should be 9 over 2. And I'm doing the exact same mistake again. Do you see that? I keep on doing this. Because I have to think, wait a minute, that can be the power to the minus. So if a snail comes by, he sees this effect. There you go. Correct. Okay, good. So that means that v is 3 over square root of 2, 10 to this. Issue? Is there an issue? This is meter per second.
It's faster than light.
It's faster than light. See that? I mean, I get the square root of 9, which is 3, divided by the square root of 2, which is 1.4 or something like that. So I get about 2-ish, 2 times the speed of light. Conclusion.
It's fake.
It's not, well, yeah. Let's put it in more physical nomenclature if you can.
This situation cannot be observed
Exactly.
physically.
Exactly. Remember that before I gave you a snippet of wisdom, as far as I have some, and then I said, you cannot have a flying bucket that for one observer is at the 2 locations at the same time. I said it requires an imaginary amount of distance. Then I said that's impossible. Here you see the same conclusion. They gave you a situation where 2 things happen at the same time, and then you find in order to see this happening, you have to go faster than the speed of light. It's the same conclusion. Cannot be done. Unless I made a mistake, and I'm not too sure that I didn't because of my minus signs and such. But I don't think I did. Now, you can also do this exercise in the space-time
But we
way.
haven't solved it yet, have we?
Sorry?
We haven't solved it yet.
Oh, no, that's true.
You
No,
want
that
to
is
solve
very
V?
true.
Gideon?
Yes.
No, we still need to use
That's not faster than the speed of light, is it? Is it
3
divided?
over...
That's gonna be smaller than 3
It
over.
is.
Help me out.
It is,
If you
1.4 is square root of
It's-
2.
if
3 over
you
1.4.
if you
approximately
evaluate it, you
CC.
get 2.12 times 10 to the 8 actually. So this is not faster than the speed of light.
Wait, help me here.
No.
The square root of 2 is 1.2, something like that. So that's
1.4 something.
Yeah.
yeah.
So you-
So the v is gonna be smaller than the speed of light
Yeah, it is.
because you're dividing 3 by something bigger than 1. So
Also, when my
Yeah,
calculator.
well, that's
gives
true,
me-
but I mean, if I would divide 3 by 1.5, I would get 2, yes?
Yeah.
And I'm dividing by something that's very close to 2. Let me put it differently. In order for this to be smaller than the speed of light, this number should be bigger than 3. And it isn't, because it's
Yeah.
1.4.
Is there any question that the numerator is bigger than the denominator?
Oh, yeah, it is. I mean, that's what I'm saying. In order for this to be smaller. Oh. No. No. Oh.
See?
We're correcting ourselves. Well, I'm correcting myself.
Mm-hmm.
You know what I was going for? Hey, it's bigger than 10 to the power 8.
Yeah.
Oh shit. Yeah.
So what is the number?
It's 2.12 times 10 to the 8.
2.12 10 to the power 8, which is smaller than the speed of light.
Yeah.
Okay, good.
We're not in trouble after all.
No, we're not in trouble after all, but I did say a moment ago that you cannot have a situation where two things happen at the same, or...
Well, you can if you're not moving with respect to that event, right?
Yes.
And in the frame that you're not moving to it.
Well, you know what
it
you know what it ultimately depends on, of course, is how far these things are apart. You can have a situation where the two firecrackers are so far apart that in order to see them happening at the same time, you have to fly from one position bringing your own coordinate system along with you. Let me rephrase. You have these two firecrackers, and you want to see them explode at the same time. The question then is there a situation possible where if one person does not see them happening at the same time, the other person does? Now, we have here a situation where apparently you can do this. But I'm pretty sure that if you play around with these numbers, you start with different starting numbers, you can make a situation where it does not happen. Yes.
If they're on the same x-axis, then if one star goes supernova and you start going with the speed of light towards a star in a straight line before it, then if it happens that it's such a time after the first event, you cause information to reach you faster by traveling at the speed of light, so you see it happen at the same time as the previous one.
Oh, wait a minute. Is that if you are going with the speed of light yourself?
Yeah.
Okay, well that is very true. If you go with the speed of light, supposing that you cannot if you have mass, but suppose that you can.
Are you talking about an inertial frame?
It has nothing to do with inertial frames per se. There's a statement that if you are going with the speed of light, then dt will always be 0. Then any two events will happen for you at the same time.
Yeah.
Okay. Okay. Apparently we have a non impossible situation.
Yeah.
Okay.
Possible situation.
Yeah, possible situation. Okay. So okay. Fortunately, thank you for the correction. I was said, wait a minute, it's close. Blah blah blah. This is correct. You have to go with about 2/3 of the speed of light. This was not the question, by the way. The question was, okay, how far apart are these things for that second observer? We now know how fast she is moving with respect to me. It's this huge number. The question now is, how many meters away does she see the things? What is the x primed? Now we have solved this one equation. I said two equations, two unknowns. We have solved one of them for that one unknown, and it gave us that number.
Yeah, you just fit it in, right?
Yeah, you just put it in one of these other twos. I would go for this one, the dx prime, of course. You have all the numbers. You plug it in, some number comes out. Now, regardless of what the number is, do you expect it to be bigger or smaller than the 3 meters of the other person? Why smaller?
Because you're going fast. I don't know, I mean, there are two events and you're moving really fast towards them, then that distance will seem shorter.
Because of Lorentz contraction?
Yeah.
I would agree with that. So I think I already know in advance that the distance is going to be shorter. Now what the number is, it's just a matter of plugging in, doing the calculation, not so important. What is important, if you go back to the way that I tried to give you some intuition on what a Minkowski line invariance means, I said, well, it just means that I can change my amount of x-ness into y-ness just by rotating, even though our distances do not change. You can also do it in space-time. That if you make distance a little bit different, it has to be compensated by a different amount of time. And that's what you see happening here. It was 0, the time distance. You rotate, quote unquote. You go to some other frame where the time is not 0 anymore, and therefore space has to compensate. Now what that compensation number is just a matter of putting that number into that second equation, find the number. Now second part of the exercise is really faster, because that's your trick. Just take the Minkowski line element, yes? I promise you, if you will just do the math, you'll find the exact same answer. And of course you should, because we derived the Lorentz transforms from that equation. Oh, we're way over. Okay. People, by tonight I will have these lectures and tutorial uploaded. I will also write a synopsis on what we've covered and where you can find it in the book, and these exercises. And what I hope to do when we see each other in a couple of days is go through the other physical exercises, see what happens.
So the homework is the physics?
Yes. Well, let me put it this way. I'm going to discuss these, and I think it's going to be beneficial if people have tried it.
Do you have more? No.